Welcome back, Year 11, Lesson 2 of Radioactivity. Please make sure you put the title at the top of page 8. Underline with the date, please. Quickly now then, we'll just go over the learning objectives for today, for this lesson. Firstly then, we're going to be learning about this term isotope. Now, isotope is something you may have learned previously in chemistry. We're then going to look at the types of radioactive emissions, alpha, beta and gamma. We won't go into too much detail about their nature today, that'll be for another lesson. And also look at why some atoms become radioactive. So it's the why they become radioactive is the important part there. And then finally we're going to consider how we treat waste materials, waste radioactive materials from nuclear power stations and other sources. Okay, let's get a move on. So firstly then, we're looking at what is radioactivity. It's something you'd have heard of. You might have recently watched a TV program, excellent TV series called Chernobyl, which gave some real insight as to what the impact of radiation or radioactivity can have on the human body. We're going to look at what happens inside the atom when an atom becomes radioactive. So I'll just go through this first paragraph with you. Radioactivity is a naturally occurring and also human-made. So when we create nuclear power stations and nuclear weapons, the nuclei of some atoms are unstable, and we're going to look at why that is in a moment. This means they have too much energy due to an imbalance between the number of protons and neutrons. They need to lose some of their energy and become more stable. There are three ways that the nuclei of most radioactive atoms can do this. And I mentioned earlier, it can happen in terms of emitting an alpha particle, a beta particle, or a gamma ray. Before we look at this information below, we're going to now use a piece of software to learn a little more. Quick recap on atomic structure: protons, neutrons, electrons and isotopes. Take this as an example. This is a hydrogen atom. You find it just there, look, in the periodic table. It's the atom with the least number of particles in it, the lightest of elements. What we can do here, we could give it another neutron. So it's got one proton, one neutron. So what we're saying is, both that atom where you've got, look, one proton or one nucleon is the same element but an isotope of hydrogen. So my isotope, hydrogen 2. So we've just created an isotope by putting in a neutron into this atom, into the nucleus of the atom. Therefore, we've got two nucleons, that's the number of protons and neutrons added together, and one proton. Here's a key, look. Protons in orange there, neutrons in grey, and electrons at orbit around the outside. And remember, you'd have the same number of electrons as protons. So there should be one electron orbiting around the outside. Now I could do that. Mass number is 2. Atomic mass. Now, the reason that's 2.014 is because we've got different percentages of naturally occurring isotopes. So this particular isotope here that we call hydrogen 2, a very small amount of that actually exists in the air. If we were to take this back out, you can see pretty much all the hydrogen on Earth has just got the one proton inside it and 0 neutrons. So let's change to let's take carbon. Carbon 12. Now carbon 12 is stable. It's got the same number of protons, 6, to the number of neutrons, 6, making it stable. If we put in more neutrons, it becomes unstable. Now carbon 14 is what we would call a radioactive or a radioisotope. A radioisotope is unstable. It's got too much energy inside it. Look up here, we've got 6 protons, but we've got 8 neutrons. We've got more neutrons and protons, making it an unstable atom or radioisotope. Now this is an important radioisotope because we use it for carbon dating, working out, or calculating I should say, or even better word, measuring how old a piece of wood or a bone is, something that was living. It tells us when anything's living, it's got carbon 14 in it, and the older something is, the less carbon 14 it's got in it. There's a tiny amount of carbon 14 existing in nature. There's a trace. If we take out some of these neutrons, you can see 1% of carbon is carbon 13. So the majority of carbon is carbon 12. Okay, 6 protons, 6 neutrons, stable. And we could do the same and look at all these different elements, and you notice all these are stable. Okay. If we take fluorine for example, look, you've got one more neutron than proton, so if we give it too many neutrons it becomes unstable. If we look at this atom, it's got the same number of protons as neutrons. There's your proton, there's your neutron. So we would say this atom is stable and therefore crucially not radioactive. So you would write down underneath here, let's get a blue pen. We know this because the number of protons and neutrons are equal. We also know that this atom has no overall charge. It's neutrally charged because we've got the same number of electrons as protons and they cancel each other out. Okay, so the number of protons and electrons are the same. The atom below is unstable. It is radioactive. So to show that, what I'd like you to do is just draw an unstable atom and put in 2 protons and put in 4 neutrons. So just now adding in the protons. Should be two protons, and so there's my 2 protons, and I'll get my red pen back. I want to put in here, that's 4 neutrons. So I've got an unstable nuclei. I know this because the number of neutrons are larger than the number of protons. So I'm going to write this in here. I've just shown that using the greater than signs. The number of neutrons is greater than the number of protons. Okay, so what happens then is that these radioactive atoms, or radioisotopes as they're sometimes called, have got too much energy in them, and they want to release this energy, or this nuclear energy. And that's where the word nuclear energy comes from. Nuclear comes from the word nucleus. And nucleus, remember, is this here. It's the center of the atom. And that energy is released 3 different ways. An alpha particle, beta particle, or gamma rays. We're going to be learning more about that later in this topic. And just for you to know, that's what an alpha particle looks like, that's what a beta particle looks like, and that's what a gamma ray looks like. If you turn over now to page 10, we're just going to consider why radiation might be a problem for humans. Radiation has only been discovered for just over 100 years. Marie Curie was one of the first scientists to investigate radioactivity, and unfortunately she contracted cancer because she exposed herself over a number of years to radioactive isotopes. If you look at this diagram underneath, it shows what can happen when radiation hits a human cell. So we've got a human cell here, and the human cell can get mutated. And the reason it gets mutated is because let's say a beta particle or a gamma ray interacts with that cell. It can lose an electron or gain an electron, and that causes the mutation of a cell. So the ionization, so that's when a cell or an atom becomes charged, causes mutation, and then that mutated cell can multiply. And that's when cancer starts. It becomes a cancerous tumour. First of all in a cell, then multiplies in a tissue, and as you've learnt, in biology, tissues make organs, and organs make organ systems. And organs make animals and humans, of course. What I want you to do now then is just pause the video and use those keywords here to form an explanation to this question. The question being, why might nuclear radiation be a problem for humans? You may well need to, if you're at home watching this video, you may well need to rewind or if you think you can answer straight away using those keywords, which I'll leave on the screen there to help you, answer now. So pause the video, change colour now. Okay, so you should have answered the question and filled in these lines here with your answer. That'll be teacher assessed. Nuclear radiation. So I've gone over these already. Just fill in these boxes. That's your alpha radiation, that's your beta, that's your gamma. The reason I'm skimming over that quickly is because we're going to be learning more about those three different types of radiation in a lesson later on in this topic. Radiation used to describe both electromagnetic waves and the energy given out by radioactive substance. Right? So as radiation is used to describe both electromagnetic waves, that's your gamma, is electromagnetic wave, and radioactive substances, that's your alpha and beta, they're particles. All of the radiation types you've written down are ionizing. They interact with atoms, can damage, kill cells because of the energy they carry. And obviously the more energy they've got, the more damaging they can be. Nuclear power stations like Sellafield. First of all, what's the job of a nuclear power station? Well, you learned about this in year 10 when we studied the topic of generating electricity. That's what they do, they produce electricity. Sellafield is in England. The largest nuclear power station in Wales, which has now been decommissioned, that means it no longer produces electricity, is northwest Wales, Trowsfynydd. They produce waste that is highly radioactive, and they remain radioactive for could be thousands of years, and stored in water surrounded by lots of concrete and sometimes lead shielding. The radiation is absorbed by these materials, that's the concrete and the lead shielding, rather than by people, making it safer. So let's look at some different ways in which radioactive waste can be stored. This one, look, underground. Here, vitrified radioactive glass, so the glass is surrounding the radioactive material, and canisters sunk into clay-filled holes. The idea that the surrounding materials absorb the radiation. What I'd like you to do now is to read this paragraph here yourself. Again, rewind this video if needed, and then answer questions 1, 2 and 3. Again, you can research this if at home, or if you've got access to a device. So pause the video, here we go, ready, fingers on buttons, pause the video now and answer the question. Okay, when you finish that, you've answered questions 1, 2 and 3. Turn over to page 12, and there's some more information there about nuclear radiation, where it comes from, and we're going to learn a little bit more now about radioisotopes. I've already explained to you earlier about radioisotopes, and that by having a different number of neutrons compared to protons makes the atom unstable. Quick reminder, as it's got here, if the number of neutrons is larger than the number of protons, the atom is unstable, making it radioactive. If the number of neutrons equals the number of protons, then the atom is stable, not radioactive. What I want you to do this time, it's going to be a self-assessed activity. So I want you to answer questions 1 to 9, and then I'm going to go over the answers, and then you're going to self-assess the answers yourselves. Okay, so pause the video when you've completed up to question 7, press play again. Pause video now. Right, let's go through these together. How many protons are present in the nucleus of this carbon atom? Well, we've got, let's count them. 1, 2, 3, 4, 5, 6. How many particles are present in the nucleus overall? So that's the number of protons plus neutrons. We've got 6 protons. Let's add them on the number of neutrons. 1, 2, 3, 4, 5, 6. So 6 plus 6 equals 12. Is this nucleus stable or unstable? Well, you've got the same number of protons as neutrons, so it is stable. Is it radioactive? No, because it's stable. Next page, we can write the information about this carbon nucleus in an easy way. We saw this earlier in the video. And remember the number at the bottom, the atomic number is 6, because you've got 6 protons. And the number at the top here is going to be 12 because it's a nuclear number, or the mass number. It's 6 plus 6, so that would be 12. If the chemical symbol for carbon is C, complete this. So you should have written down C612. How can you tell? Right, question 6. Could you mark these, please, as you're going along in a red pen, of course? How can you tell that this is the nucleus of a carbon atom? It's the number of protons that tell you which element it is. So the answer there would be, it has 6 protons. If it had 7 protons or 5 protons, it is no longer carbon, it's a different element. What's the mass / nuclear number of this nucleus? Let's just check now. We've got 1, 2, 3, 4, 5, 6 protons. 6 protons. How many neutrons? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 neutrons. So we've got 14 nucleons altogether. So the mass number or nuclear number is 14. What's the atomic number? The atomic number is the number of protons. It's that there. So the atomic number is 6. Write out the same information for this atom using the same format as in question 5. That's this here. Same format. Here we go. Oh, let's do a nice little rectangle to put it in first. There we go. And we've got, it's a carbon atom still, so we still use that symbol. It's got 6 protons at the bottom, the atomic number, but the number at the top now has changed to 14. That's your mass number. Remember to mark with a red pen. Turn over now, please, to page 14. Now you can see here we've got, again, 2 nucleons. Let's just do a bit of counting. We've got 1, 2, 3, 4, 5, 6 protons. We've got 1, 2, 3, 4, 5, 6 neutrons. So this is our stable. This is a stable carbon atom. It is not radioactive. Let's compare. We've got 1, 2, 3, 4, 5, 6 protons. 1, 2, 3, 4, 5, 6. 8 neutrons. This is an unstable carbon atom. I'll call it a radioisotope. it has 2 more neutrons than protons. So a quick summary. This is important. If the number of protons is less than the number of neutrons, I want you to finish that sentence, please. Just think back to what we've learned. When you finish that, turn over the page to page 15, another self-assessed activity. Let's see how far we go up to question 9. Yeah, question 9 is the last question of this lesson. When you finished, so you're going to pause in a moment. When you finish question 9, press play and mark your work. So press pause. Ready for it? Now. Okay, let's go. So if we look at Z, you can see a number of protons at the bottom, 15. My 5 looked a bit like a 6 there. Question 2, number of neutrons in X. This takes a little bit more thinking about. To work out the number of neutrons, this one here, that's the number of protons plus the number of neutrons. And we can see there's 15 protons plus a certain number of neutrons equals 43. So the number of neutrons, we'll call N, is 43 take away 15. 43 take away 15 will give you 28. 28. Here we go. Which element is an isotope? Now an isotope, remember, is where we've got that different number of neutrons to protons. Right, question 3. Which element is an isotope of Z? It would have to be X because they've got the same number of protons. Which of these elements are radioactive? How can you tell? Well, remember, if you've got a larger number of neutrons than protons, it's radioactive. So if we look at Z, Z is because it has 15 protons and how many neutrons? Well, it's 48. Take away 15. That's going to give you 33. I did that back to front really. I should have worked out the number of neutrons and protons and then decided if it's radioactive or not. So I'll do that now for Y. Y has how many protons? 16 protons. How many neutrons? Well, I'll have to do 48 take away 16. It's 32. 16 protons and 32 neutrons. Therefore, it's a symbol for that. Therefore, it is radioactive. So I skimmed over that bit there. That's a symbol for therefore. Therefore, it is radioactive. Let's do the same now for Z. Z has, I think we've we've done Z. X has 15 protons. We've already worked it out. 28 neutrons. Same again. Therefore, it is radioactive. How many electrons are there in Y? Well, it's the same number as the number of protons. So that's 16. What's the nucleon number of X? Nucleon number is this one at the top, 43. What's the atomic number of Y? That's the number at the bottom here, 16. That's the number of protons, remember. The mass number is the same as the nucleon number. So that's the number at the top. Mass number of Z, 48. And finally, an isotope of uranium contains 92 protons and 146 neutrons. Its chemical symbol is U. Complete the mass and atomic numbers below. So we've got 92 protons. That goes on the bottom. So the number on the top, we'll have to do a quick bit of maths. 146 plus 92. Get my ruler. I could use a calculator for this, couldn't I? We'll do it two ways. 6 plus 2 is 8. 9 plus 4 is 13. Carry the 1. 238. Let's check that with a calculator. 146 plus 92, 238. So that's the answer you put at the top there. Mass number, atomic number. Remember, the mass number is sometimes called the nucleon number. We'll finish there in this lesson. Make sure you watch the additional videos and complete the plenary assessment. See you next time.